Hello again and welcome to a new lecture in which we will do an example to illustrate the application of the second moment of area and the parallel axis theorem for a composite section, for a composite area. But before we start the example, the question that comes to mind is, what is the meaning of the second moment of area? What does this mean? What does it mean that a section has a larger second moment of area than another one? Well, firstly, let's look at the actual area versus the second moment of area or the moment of inertia. And the first thing that we note from their expressions is that both are geometric properties of figures. Both are geometrical properties of figures. Now, let's step back a little and recall that the axial stress for a member under axial loading, sigma, was equal to the force, the axial force, divided by the cross-sectional area. So for that member, for an axially loaded member, the cross-sectional area measures the capacity of a member to resist axial stress. The larger the area, the smaller the axial stress, so the less likelihood that the axial stress will reach or exceed the capacity, the maximum stress that the member can sustain. A larger cross-sectional area, a stronger member. Now, in the next few lectures, we will also learn that the bending stress of a member that is in bending has a similar expression, in the sense that sigma, the bending stress, equals to the moment divided by the moment of inertia times y, in which y is a parameter. We will learn about that in the future. But if you look at this formula, it very much resembles to the one for axial stress, in the sense that it results that the second moment of area, or the moment of inertia, if you want to call it like that, now measures the capacity of a member to resist bending stresses. So in other words, the larger I is, the smaller the bending stresses, so the less likelihood of these stresses due to bending to reach the capacity of the member, so the maximum allowable or yield bending stress. Okay, but we will learn about these in the future. What you need to remember is the difference between A and I. One measures the capacity of a member to resist axial forces. The other one measures the capacity of a member to resist bending or bending moments. Having said that, let's go now and solve an example. An interesting example that requires us to determine the moments of inertia for an I-beam. So a beam that has a cross-section similar to the capital letter I. So let's draw this section quickly. The top flange, the web, and now the bottom flange, like so. So now you can see it's not a rectangular shape, it's a more complex shape. Let's add some dimensions. So the thickness of the flanges is 20 millimeters and the height of the web is 400 millimeters. And also the width of both flanges, same width, is 200 millimeters. And finally, the thickness of the web is 10 millimeters. Now, if you look at this section, it has two axes of symmetry. So therefore, we do not need to determine the location of the centroid in either direction. Remember that by definition, the second moment of area must be calculated about the centroidal axes. So now, because this section has two axes of symmetry, which is x and y, as shown in purple, running right through the middle of the section in both horizontal and vertical directions, and there's no need to determine their location anymore. We know they're located right in the middle. So the axes of symmetry, as we've learned recently, in this case, are also centroidal axes. So therefore, the question now asks that we determine the moment of inertia about the x and y axes. And again, we know the location of these axes for the entire section. They're in the middle along both directions. However, we cannot calculate this directly because we don't have a formula for this kind of shape, an I shape. So we need to divide this composite section into simpler elemental areas, and it's very straightforward to notice that we can divide this section into two rectangles, number 1 and number 2, which are identical, and these are the flanges, plus a third rectangle, which is number 3, which represents the web of the section. Now, we will have to calculate the second moment of area about the local centroidal axes for each of these sections. So each of these three sections has its own centroid. So I'm drawing now their own local axes in red. And you may notice that because the flanges are rotated, the axes are also rotated. So the x-axis is vertical, the y-axis is horizontal, such that for these elemental areas 1 and 2, Ix will always be larger than Iy, which is by convention. The other parameter that we need is t, the distance between the centroidal axes of the individual elements and the centroidal axis of the entire section, and these are equal at the top and bottom. They're both equal because of symmetry to 210 millimeters. Now we can proceed to calculating Ix. We have two flanges, so 2 times the I flange about the own centroid plus the transfer term AT squared, where t is calculated from the own centroid of the flange to the centroid of the entire figure, plus the moment of inertia of the web about its own centroid, which in this case coincides with the centroid of the entire figure. So t will be 0 for area number 3. So there will be no additional transfer term. If we put this into numbers, so again 2 for the two flanges, 200 times 20 cubed, right? The distance perpendicular to the axis about which we calculate the second moment of area, which in this case is y for the local axis of the flanges, plus the area of the flange, 200 times 200 times transfer term, 210 millimeters squared, plus the contribution of the web, 10 times 400 cubed. Again, the dimension perpendicular to the axis, to the x-axis, is cubed, divided by 12. Now, if we calculate these terms, we get these numbers like so, and if you add these numbers together, the total for Ix will be 406 times 4.4 times 10 to the power of 6 millimeters to the fourth. It's very common to express the moment of inertia in terms to the 10 to the power of 6 millimeters to the fourth, so that we end up with a nicer number before the exponent. Now, if you look at these three components, you will see that the transfer term dominates. It's the largest number. in the composition of Ix, and that's because material was pushed away from the centroid of the entire section. This is how these flanges were created. So material was pushed away from the main XX axis. The more you push away, the farther you push away, the larger the transfer term will be, and therefore the larger the resulting moment of inertia. That's why this shape, the I shape, and it's a very commonly used shape in structural and mechanical engineering, just for this reason. Now, on the other direction, Iy is much simpler to determine, just because the centroid of the three elemental areas 1, 2, 3 correspond with a centroid of the entire section in the horizontal direction, so there will be no transfer term. So here you can see the contribution of the web and twice the contribution for the flanges. And in the end, the total moment of inertia for the y-axis is 26.7 times 10 to the power of 6, again, millimeters to the fourth. You can see again that Ix is much larger than Iy, and this is because, of course, due to the moving of the material away from the centroid in the y direction, so perpendicular to the main axis x of the section. So this is how the parallel axis theorem is being applied to calculating the moment of inertia for a composite section. Thank you very much for watching this lecture, and I will see you at the next one.